KSP, the solubility product constant. In a saturated solution, you will have an equilibrium between solid ionic compound and aqueous ions. And no more of the ionic compound can dissolve in solution. As soon as one set of ions dissolves, another set of ions goes back to the solid state. So the forward and reverse reaction are happening at the same rate, and you have your ionic solid and your saturated solution up above it. Now in this case, our ionic solid is some hypothetical one where the cation is M with a charge of B+, and there's A of them in the formula, right? So when it dissolves, you get A number of M B+ ions, right? So that's your cations. And you also have the anion X, which has a charge of A-, and there's B of them. So when it dissolves, you get B number of A- ions. So let's look at an actual saturated solution. So let's say our ionic compound is calcium phosphate. So we'll have 3 moles of aqueous Ca2+ ions, and we'll have 2 moles of aqueous PO4 3- ions. And so the question is, what is the concentration of the ions in solution? So the answer is you use KSP. KSP is the equilibrium constant, right? So the general form of KSP for the hypothetical solution is KSP equals the concentration of cation raised to the 8th power times the concentration of anion raised to the bth power. Note that we do not include the solid because we only put things whose concentration changes in an equilibrium expression, and solids and liquids don't change. To actually see how this works, we should do a real example. So what's the concentration of a saturated solution of calcium phosphate? A quick Google search reveals the KSP value for calcium phosphate is 2.07 times 10 to the negative 33rd. So here is the equilibrium. We've got solid calcium phosphate in equilibrium with 3 moles of aqueous calcium ions and 2 moles of aqueous phosphate ions. And think about it. Say X moles of calcium phosphate dissolves. Then you get 3X moles of Ca2+, and you get 2X moles of PO4 3-. We then write the equilibrium expression. KSP equals the concentration of Ca2+ to the 3rd power times the concentration of PO4 3- to the 2nd power. So 3x to the 3rd power times 2x to the 2nd power equals 2.07 times 10 to the negative 33, our KSP value. So this equals 3 cubed times x cubed times 2 squared times x squared. 3 cubed is 27. 2 squared is 4. And x cubed times x squared is x to the 5th. So we get 108 x to the 5th power. So now we need to solve for x. And so we're going to divide each side by 108 and take the 5th root. So we have x equals the fifth root of 2.07 times 10 to the negative 33 divided by 108. And when I plug that in, I get 1.14 times 10 to the negative 7th. So that's X, and that is the molar concentration of calcium phosphate in solution. So we say the solution concentration, bracket solution, is equal to X, which is 1.14 times 10 to the negative 7th. But what if we want to know the concentration of calcium? And what if we want to know the concentration of phosphate? Are these simply equal to X? Not quite. They're X times the subscript. And the subscripts we're talking about are the subscripts in the chemical formula, Ca3PO4 2. So we multiply X by 3 to get the concentration of calcium, and we multiply X by 2 to get the concentration of phosphate in solution. So the calcium concentration is 3 times 1.14 times 10 to the negative 7th, which is 3.42 times 10 to the negative 7th molar. And the phosphate ion concentration is 2x, or 2 times 1.14 times 10 to the negative 7th, which gives us 2.28 times 10 to the negative 7th molar. So here's an exercise for you to try. What's the molar solubility of HgBr2? In other words, what's X? And then what is the concentration of mercury ion and the concentration of bromide ion in a saturated solution of HgBr2, given that the Ksp of HgBr2 is 1.3 times 10 to the negative 19th. Pause and work it. Here's the answer if you are ready. So, if X moles of HgBr2 dissolves, then we get X moles of Hg2 plus and 2X moles of Br minus. And so we have Ksp equals X times 2X squared equals 1.3 times 10 to the negative 19th. So we have 4x cubed equals 1.3 times 10 to the negative 19th. Just because the whole quantity 2x squared is 2 squared times x squared, which gives you 4x squared, and x squared, or 4x squared times x is 4x cubed. So now we want to divide both sides of this equation by 4 and then take the cube root. And we get x equals the cube root of 1.3 times 10 to the negative 19th divided by 4. So on the calculator, we get x equals 3.2 times 10 to the negative 7th. That is the molar solubility of mercuric bromide, HgBr2. Now, what's the concentration of Hg2 plus? Well, it equals X, so it's 3.2 times 10 to the negative 7th molar, What about the concentration of Br minus? Well, that equals 2x. So that is 6.4 times 10 to the negative 7th molar. Good job.